Hi, in this video we will consider principal operation of two different computational platforms that can be used for real-time algorithms implementation. In particular, we will focus on central processing units, CPUs, and field programmable gate arrays, FPGAs. Any computational system consists of three main subsystems: processing, storage, and communication. Processing subsystem is responsible for performing actual calculations. Storage subsystem provides data and stores computation results. And the last one, communication, is responsible for transferring data between different levels of memory hierarchy within the storage subsystem. Okay, and now keeping this triangle in mind, let us consider principal operation of CPU. The blue block in the middle is arithmetic logic unit, ALU. Obviously, ALU is a processing subsystem, and this ALU is surrounded by a bunch of yellow blocks, and yellow blocks are they belong to the memory subsystem. On this picture we can see random access memory, intermediate cache memory, and a set of registers. And this memory hierarchy can be described by the trade-off between capacity and the access time. So the random access memory is the largest one, and however it takes a long time to read data from random access memory. And the registers, they are the fastest, but at the same time they have the lowest capacity. And on this picture the communication subsystem is not shown, but it is implied that the data can be transferred between different levels of memory hierarchy. For example, we can transfer data from RAM to cache and from cache to registers and back. Okay, now let us assume that we want to add two numbers together, two numbers A and B, and we assume that they are stored in the random access memory. Let's say we want to add them together. So in order to do this, processor will transfer the data to the registers so that these two numbers can be added by the arithmetic logic unit. So we see A and B traveled through the whole memory hierarchy from RAM to cache, from cache to registers, and once they reach the registers, they can be processed by arithmetic logic unit. Okay, once we get the result, perhaps we will want to store it back to the random access memory so that we can use it for further operations. Okay, based on this animation, we can notice several things. First of all, the significant amount of time was spent on transferring data, while the actual calculation was relatively fast. This is the first important thing. The second thing is that the architecture of CPU, it is fixed. So we see that there is a size of random access memory that we cannot change, fixed size cache and registers, and we can do nothing about this. In other words, we cannot tailor the architecture of CPU with respect to our algorithm. And also we can notice that we performed addition operation, while arithmetic logic unit has different arithmetic and logic operators that are not used for this particular application. This means that that processor has redundant logic that is not used for our particular algorithm. Okay, now let us compare this to FPGA approach. In contrast to fixed architecture CPU, FPGA is just a set of logic blocks that are connected via switch matrices. And by configuring these switch matrices, we can build any architecture that we want. So we can tailor the architecture with respect to the algorithm that we are trying to implement. Okay, coming back to the example of adding two numbers. Okay, we will generalize this example for the vector case. Let us assume that we have two vectors, 4 elements each, and we want to add these two vectors element-wise. With FPGA approach, we can synthesize memory for our particular application. So in this case, we know that we have 4 elements, and we can synthesize memory exactly for these particular vectors. So for this example, we synthesize 2 memory blocks for 2 vectors, for 2 input vectors, and 1 memory block for storing the result. Another important thing is that in terms of computational logic, we synthesize only addition unit, and we don't synthesize any other units that are not used for this particular algorithm. And keeping this in mind, we will run the animation to see what happens inside FPGA. Okay, since memory block is connected directly to the computational unit, we can read data within 1 clock cycle and start computations immediately. Moreover, while we are computing the first vector, we can start the first element from the vector, we can start computing the second one. And this technique is called pipelining. So every clock cycle we get a new piece of data. Pipelining is widely used in FPGA implementations, and it is an efficient technique to speed up computations and to increase the throughput. In addition to pipelining, since we have full flexibility of tuning the architecture, we can partition memory blocks, and we can synthesize several computational units. So instead of having this architecture, we can partition our arrays. We can replicate computational units in order to parallelize computations. So FPGAs allows us pipelining. FPGA allows parallel execution, and since both memory and computational subsystems are flexible, with FPGA approach we can try different data representation types. For example, instead of using standard double precision floating point, we may want to consider single precision floating point or even fixed point arithmetics. So to sum up, FPGA, the main things that we can do with FPGAs in order to speed up computations are pipelining, parallelization, and tuning data representation. Thanks for listening.